Well, good afternoon. It's 12:17 on Monday, the 29th of October, 2018. It's supposed to be Cal 3 class right now, but right now I'm the only one in here, so I guess I'll go and get started from where we left off last time. Let me just mention one kind of a minor announcement. I apologize for having to do this one, but we are in the middle of trying to get the final spring and summer schedules worked out, and the spring schedule has been an awful mess, and it's taken way more time than I thought it ever would to get done. So I am a bit behind in grading, and certainly even further behind in getting things on Blackboard. So most of the paperwork that you've turned in so far, I think, has been graded. The trouble is I don't have anything on Blackboard yet recently. So I'll try to get it as soon as I can. I'm hoping this afternoon. I've got 4 hours, supposedly have 4 hours of office hours. I haven't finished eating, so it'll take me just a little while to finish eating lunch. But after that, hopefully most of 3 to 4 hours of office hours. I do have one student I know coming by, but possibly another. But other than that, I hope I'll be able to get a lot done on getting the spring schedule at least further along the way than it is now. Hopefully I can get the one really bad class, I've gotten all those straightened out. I think the second one that was almost as bad, I'm probably close to halfway getting that straightened out, and then the rest of them are not going to be that bad, I don't think, to do. Still have summer to go, but I think I can hold off on summer and start grading again, and then come back and finish on summer, because we won't be registering until summer, until midterm in spring, so I'm going to let that one sit for a while. Okay, let's pick up where we did last time. We're in Chapter 13, Functions of Several Variables. 13.5, Chain Rules for Functions of Several Variables. We had just started this section and done example 1, and where we are on the slide here is basically at the top of page 912. The chain rule in Theorem 13.6, which was the lead-off theorem in section 13.5, can be extended, provide alternate techniques for solving many problems in single variable calculus. For example, in example 1, which we just did, you could have used a single variable technique to find dw dt by first writing w as a function of t, and I think we did that. I think I did that right at the end of class and showed you could do it without going through the chain rule of different variables. But they all work, the same. Okay? So if you can write, sometimes you can't, but sometimes you can write all of, for instance, this is w, a function of x and y, but x and y are both functions of t, so you can substitute in what your function of t for x and y are, plug those in, and then do your dw dt without having to go through the partial derivatives. Okay? Not saying it's any easier or harder. Sometimes it works better one way and sometimes another. So, yeah, I think we did that last time. If not, and you need me to do it, I'll be glad to show you that again. So let's move on to, I was going to say example 2. Actually, I guess that we just did. Okay, sorry. That last slide was the bottom part of page 911. I was thinking that was the top part of 12. Bottom part of 911, and I think we did do that. Okay? And then this is the top part of 912. Okay? The chain rule in Theorem 13.6 can be extended to any number of variables. And for example, if each of the x of I is a differentiable function of a single variable t, then w is equal to some function of x of 1, x of 2, x of 3, up to x of n. Then you have dw dt is the partial of w with respect to x of I times derivative of x of I with respect to t, plus the partial of w with respect to x of 2 times dx2 dt, and so on up to partial of w with respect to x of n times dx of n dt. Just simple extension of what we were just doing. Okay, they're skipping example 2, so let's go back and find some room to do example 2. All right, two objects are traveling in elliptical paths given by the following parametric equations. So here, let me get my pen set up. Okay. Here is the first. X of 1 is equal to 4 cosine t, and y sub 1 is equal to 2 sine t. X sub 2, the second parabola, ellipse, okay, 2 sine 2t, and y sub 2 is equal to 3 cosine 2t. Okay. First object, the subscript 1, second object, subscript 2. Two different elliptical paths, okay? At what rate, sorry, I've had a lot of trouble with drainage today, I don't know why. At what rate is the difference between the two objects changing when t is equal to pi? So we're looking for at what rate is the distance changing? Between the two objects changing with when t is equal to pi. Okay. Now rate of distance, that would be, excuse me, wow. You're going to need to compare basically your distance formulas here, okay? Sorry, I'm having trouble getting my, I was just trying to finish eating before lunch, before I came to class, and my whole system is awfully dry. I didn't obviously drink enough. I thought I did. So I'm having trouble getting my voice to come back well. Okay. So, what rate is the distance changing between the two objects? Okay. So we've got to figure out what the distance between the two objects is. Okay. Well, the distance between x1, y1 and x2, y2. That's what we're looking for. That is the square root, so the distance formula is the square root of x, and it doesn't really matter which one you put first or second. I think they do x2 minus x1. It doesn't really matter. x2 minus x1 squared plus y2 minus y1 squared. Okay, and as you see, it doesn't matter, because if you reverse the x1 and y1, x2 and y1 and y2 and y1, you're squaring them anyway. So there's not any difference there in that distance formula between which one you put first and second. So don't sweat that any. Okay, And the rate at which the distance is changing, this is the distance at any time t that they're apart. So the rate at which they're changing is d. Boy, I don't like this one. And what they did in the text to avoid this problem, they didn't call this distance d, they called it s. Okay, makes it a lot easier because now you're looking for ds dt. How is the distance changing? What is the rate of the distance change? And then we'll come back and plug that in. All right, well, before we do that, let's rewrite this as x2 minus x1 squared plus y2 minus y1 squared quantity to the 1/2 power. If we write it that way, I think it'll be a lot easier to see how we do the dy dt, ds dt. Okay. Now, there are times, and this is somewhat of a strange problem here, they do draw a picture here, which I don't really want to draw, but please look at it in the book, okay? And you see they pick a few somewhat sort of random type times to compare this. They look first at time t equal pi thirds, and then t equal pi halves, and then t equal pi. And we're interested in what's happening at t equal pi. Okay? Now, what they do is usually not done. Okay? I really don't like this technique, but it is okay in this. When t is equal to pi, before we do anything else, they're going to plug in and show you what the displacement is then. Okay? When t is equal to pi, so x of 1 when t is equal to pi is cosine of pi is -1, so that'd be a -4, and y sub 1 of pi would be 0. Okay? X sub 2 at pi is 0, and y sub 2 at pi, I can't write, I don't know why, this is so hard to get this to do properly. Okay, that would be 3. Okay. Now, most of the time we don't start plugging in until we have done our calculations. But they just wanted to show, I think, what these were, and since those are the values, the distance apart, which would be s at pi, would be the square root of 16 plus 9, which is equal to 5. Okay? Now, Okay. So they start with that. That's where you are. That's the distance apart at time t equal pi. I don't think I would have ever thought or planned to start the problem that way. Okay? So then they say at t equal pi the partial derivatives are as follows, and then they give what those partial derivatives are. That to me is where you should have started. Okay? And that's why I wrote it in this form. And what is ds dt? That would be the partial of s with respect to x times dx dt plus the partial of s with respect to y times dy dt. Okay. Now that's what we were doing before, and that seems like it makes a lot of sense to do. I'm sorry about that. Okay. Now, if you're doing these partials, the partial of s with respect to x, that would be, and that's where they launch into stuff here, that would be 1/2 times x2 minus x1 squared plus y2 minus y1 squared to the minus 1/2 times the derivatives, and that would be 2 that'll be the best way to say this, 2 times x2 minus x1, okay? Now, that's the partial of s with respect to x, okay? You do the outer first, 1/2 this to the minus 1/2, then the derivative of the inner, chain rule derivative of the inner. That'd be 2 times that. Okay? Now, that's just partial with respect to x, partial of s with respect to x. You can do the same thing for the partial of s with respect to y. The only difference is here it'll be 2 times y2 minus y1. Okay? Same denominator. Okay? So all that is the same. And one thing you might note, you can cancel out the 2's there. So that makes it a little easier. Cleans it up just a tad. Okay? And you can do the same plugging in then at t is equal to pi. Those are still going to be those same values, so nothing really changes there. That will give you the rate at which s is changing with respect just to the x variable, okay? And then do the same thing for the y, okay? And then do your dx dt and the dy dt, and you can get the total change, you might say. And I just don't have enough room to write all that down. Let me just try to do this part. Partial of s with respect to y is going to be the same type look to it, that would be x2 minus x1 squared plus y2 minus y1 squared to the minus 1/2 times x2 minus x1. Okay. I'm sorry, y2 minus y1, because that's chain rule with respect to the second one. Okay. I can't get the pen to come back. There it comes. y2 minus y1. Okay. Now, and then, of course, you can do your dx dt and dy dt. Those are pretty straightforward. You do it for both x1 and x2. I'm trying to figure out why in the world they're wanting to do this anyway. Okay. Okay. And again, this isn't the standard protocol for doing this, but it's what they're looking for in this problem, is the change of the partial of s with respect to x at this particular value. Okay, that's the rate of change of s with respect to x, and then we'll multiply that by dx dt. But we do this for each of the x's, x1, x2, and then we'll do it for y1 and y2. So it really is going to take up a lot of room to do, and I'm afraid we're just going to get totally lost there. As you see, it takes an entire page in the book to get this done. And I've set it up. You just got to plug in the values here. Except the only thing... Okay. Yeah, one other minor thing, but it is doing. Each of these is with respect to x, so you got x sub 1 and x sub 2. When you're doing x sub 1, you introduce a minus sign because of the chain rule here. That part's still the same, but then you have, when you're doing partial of x s with respect to x1, then you get an additional, let's see, that's probably not how I want to do it. You put an additional minus in front of it, okay? And when you do it with respect to y1, that is also going to have an additional minus in front of it. You do it with respect to x2 and y2, because they don't have that sign, then you don't have to worry about those, okay? Now, and notice that the partial of s with respect to x1 is just the opposite, like negative 4/5, of partial of s with respect to x2, which is positive 4/5. when you plug in all those values. And same thing for y. Partial of s with respect to y1 is minus 3/5, where the change of s with respect to y2 will be the positive 3/5. Okay? And then when you're doing your dx1 dt, dy1 dt, dx2 dt, and dy2 dt, you have to do each one of those separately as well and plug them in at pi. Excuse me. And you know, it's going to take probably 3 times the screen that I've got to write on. So you just basically do each one of the things separately. And let me go back and restart parts of this anyway. Because in effect, you have 4, you don't quite, but it's sort of like you have 4 independent variables here. x1, x2, y1, and y2. Okay? So when you're doing the partials here, we've already done this part, and I hate to erase it, but I just have to in order to have room to write. This actually expands to be partial of s with respect to t, partial of s with respect to x1, dx1 dt, partial of x with respect to y1, dy1 dt, plus partial of s with respect to x2, dx2 dt, plus partial of s with respect to the can't get this thing to disappear. There it goes. Okay. Partial of s with respect to y. This isn't writing well. 2 dy2 dt. My pen is really slow. Okay. So you see you actually have 4 of those partials to do, and then your ds dt will be the combination of all those. And it's not an impossible problem. It's very straightforward, but it just takes step after step after step and line after line and page after page to write it all down and get it to work well. They work it out in the book, and I think that's all we have time to do and room to do, because by the time I get halfway through that, I'd need to have something that I'd already erased, and most of what you need is right there in front of you now, I think. Okay, so let's move on to example 3 if we can. Okay, so let's get out of example 1 here. And we've already done that and that. Okay, no, going to have to do example 3 ourselves also. So let's go back and do example 3 here. Hopefully we'll get a little better resolution than we got with example 2, though it was fine. All right, here's example 3. Find the partial of w with respect to s and the partial of w with respect to t for that was supposed to be a w. for W is equal to 2xy, where x is s squared plus t squared, and y is s over t, which I like to write as st to the minus 1. Okay, just t to the minus 1, not the st, but just the t. I'm sorry, I don't know why it's doing this, but I'm just having trouble getting the vocal cords to work well. Basically, a lot of drainage. Now, here's something different about this one. Notice the W, as before, is a function of x and y, as you see here. But now your x's and your y are not just variable of a single function of a single variable, they're functions of two variables, s and t. So now, rather than total derivatives of your x with respect to s, you have a partial with respect to x of x with respect to s, and a partial of x with respect to t, partial of y with respect to x, and a partial of y with respect to t, which was not quite the same as what we had in the earlier examples. Okay? So there's a couple ways you can go with this, and perhaps the easiest in this case is just plug in what these are. Now, sometimes you can do this and sometimes you can't, but let's express W as a function of s and of t. Well, here it's only expressed as a function of x and y, but here x is expressed as a function of s and t, and y is expressed as functions. So the W equal to 2 times s squared plus t squared, that's your x, okay, times, and your y is s over t. Okay. Oh, man. Okay. This could be written as 2s cubed over t plus 2st. I believe that's right. Okay. Now, that's not an impossible thing to take the partials with respect to. This is your W, and that would be the partial of W with respect to s would then be 6s squared over t. Because you treat the t as if it's a constant, plus 2t. Partial of W with respect to t. Alright, this is a little messier. I think I would rather write this as 2s cubed t to the minus 1. Okay, so the partial of W with respect to t then would be minus 2 s cubed t to the minus 4. Okay. Okay. I'm going to have to pause for just a minute and go clear my head. Thought I'd be able to oops, that's not the one I want to do. Pause. Pause. All right, sorry about the delay, but my head was getting so clogged up, and I was really getting dizzy. And I still can't talk well, but I cleared out a lot of stuff. Anyway, let's get back to this. Sorry, I had to stop in midstream here. Still can't talk. Sorry. So, yeah, in fact, I was right in the middle of this. The partial with respect to W with respect to T, from the first one here, that's a minus 2s3, I'm sorry, s cubed. I don't know where that negative 4 came from. That's negative 2. Sorry about that. Okay. Plus the partial of this with respect to T, which is just 2s. Okay. All right. So there's the partials of W with respect to S and T like they called for it. Now, they do a little more processing on them, you might say, by putting them over least common denominators. And they factor out the 2 as well. I don't see any big advantage of it. Then they put it back in. So let's just leave it where it is. That would be 6s squared plus 2t squared over t. And this one would be, let's rewrite this as minus 2s cubed over t squared, and then write that similarly, and that would be minus 2s cubed plus 2s t squared over t squared. So that's written on least common denominators. I think that's how they have it in the book as well. 6s squared plus 2t squared over t, and then the dw partial w with respect to t would be 2s, well, they reverse the order, 2st squared minus 2s cubed over t squared. Okay? Now, the next theorem that comes up is going to give an alternative method for finding partial derivatives without explicitly writing w as a function of s and t. See, they chose to do this first, which I found unusual to do that to begin with. Why didn't you just do the chain rule? But that's what the next theorem is going to do. So here then is that next theorem. Let's scroll on through here. And here's the chain rule for 2 independent variables. Before, we only had ultimately 1 independent variable. There were 2 or maybe even 3 intermediate variables, okay, but only 1 independent variable. Now we have 2. So here's theorem 13.7. If w is some function of f of x and y, excuse me, sorry, I've still got problems, where f is differentiable function of both x and y, and if x is a function g of s and t, and y is some other function h of s and t, so those are both, each of them are functions of 2 separate independent variables, such that the first partials, partial of x with respect to s, and the partial of x with respect to t, the partial of y with respect to s, and what partial of y with respect to t, all exist, then you can talk about the partial of w with respect to s and the partial of w with respect to t. And I would hope this is exactly what you would expect it to be. Partial of w with respect to s would be the partial of w with respect to x, but then the partial of x with respect to s. Now that looks a lot like what we did before, but before this was just a single variable here. This was a single variable, so this was a full derivative, not a partial. That was a partial, and this was a full. But now since x and y are functions of two variables, those are now partials. So they look just like they did before, except you have partials in every place, not just in one. So plus the partial of w with respect to y times the partial of y with respect to s. And then you do it the same thing for t, partial of w with respect to t, partial of w with respect to s times the partial of x with respect to t, plus partial of w with respect to y times the partial of y with respect to t. And that's the basically the chain rule when you have two independent variables, okay, rather than just one ultimate independent variable. And they like these little diagrams, I guess you would say. Partial of w with respect to x times the partial of x with respect to t times the partial of, plus the partial with respect to well, they have kind of rearranged things a little bit here. The partial of plus the partial of x, partial of w with respect to x times the partial of x with respect to t, plus the partial of w with respect to x times the partial of x with respect to s. That's what we had here. And partial of w with respect to y times the partial of y with respect to t, plus the partial of w with respect to y and partial of y with respect to t. The problem with this diagram is it pieces together. Usually you do this part here and this part here, the t's together and the s's together, whereas this makes it look like you do the x's and y's together and separate out the others. I don't really care for their schematic as much. It is correct and everything, but it's not the same order that you usually do things with the chain rule. Okay, so let's move on from there, and I think example 4 is going to use that. Use the chain rule to find the partial of w with respect to s and the partial of w with respect to t for this function we just did, exactly the same function we just did, but this time we're going to use the chain rule, not solving for w for as a function of only s and y, removing the x's, s and t, removing the x's and y's. Sorry. Now I've got, and again, I like to rewrite this as st to the minus 1. That just makes it easier to do everything you need to do, pretty much. Okay? So, partial of w with respect to s is the partial of w with respect to x times the partial of x with respect to s plus the partial w with respect to y times the partial of y with respect to s. Okay, so let's come up here and do the various pieces. Partial of w with respect to x is 2y. The partial of w with respect to y is 2x. Okay? Let's do these pieces as well. Partial of x with respect to s is equal to 2s, and the partial of x with respect to t is 2t. And partial of y with respect to s is t to the minus 1, and the partial of y with respect to t is equal to minus s t to the minus 2. Okay, those are all the little pieces. Now let's plug them back into here. Partial of w with respect to s is partial of w with respect to x, 2y, partial of x with respect to x, times 2s, okay, plus partial of w with respect to y, 2x, times partial of y with respect to s, there it is, t to the minus 1. Okay? Now, you want this expressed just in terms of s's and t's. You don't want the x's and y's in there. So now we plug these values for x and y into this. So this would be 2s over t. I'm going to put it back this way. Times 2s, okay, plus two times s squared plus t squared times, I'm just going to put it over t, okay. So there's your partial of w with respect to s. Let's clean it up a little bit. 4s squared over t plus 2s squared over t plus 2t, which would be 6s squared over t plus 2t, which, if you go back to the first solution, well, one exception. Put it all over least common denominator, 6s squared plus 2t squared over t. That's exactly what we got in the first part of example 4. All right. Now, if I have room, I'm going to try to do this too. Partial of w with respect to t would be the partial of w with respect to x. We already know that. That's our 2y. But the 2y is 2s over t, just like it was there, times, but now it's the partial of x with respect to t. And the partial of x with respect to t from the one up here is 2t. So this would be 4s yeah, 4s, okay? That doesn't seem right. No, that's not all of it, sorry. We'll come back and do this 4s. Goodness, this isn't erasing. Yuck. Okay. I've got more to write. I've paused there too soon. Okay. Plus the partial of w with respect to s is the partial of w with respect to x times the partial of x with respect to t, which that's the part we did, plus the partial w with respect to y, which is exactly what we had before, to x times partial of y with respect to t. The partial of y with respect to t was up here, and this would be times of minus s over t squared. Okay, from up there. Now we take these and oops, sorry, I meant to plug in the x here too. Okay, your x was s squared plus t squared. Okay. All right. So what does this become? 2s plus, no, 4s, sorry. Forgot my second 2. Okay, 2 times 2, okay. 4s plus, actually, we'll make that a minus. Not looking far enough ahead. Okay. Uh, 2s cubed over t squared minus 2st squared. No, just minus 2s. Because it's t squared over t squared. Okay. Now, this becomes 4s minus 2s is 2s minus 2s cubed over t squared, which would be 2st squared minus 2s cubed over t squared. Okay, which you'll see the bottom part, this is dw dt from before too. 2st squared minus 2s cubed over t squared. So we came out with the same. I had to do some earlier substitutions in there, but just because it was so I have such room restrictions, you know, on what I can write on the thing. Now, okay. All right. I was trying to see where they all right. Okay, I'm sorry. Oh, wait. All right, sorry. I'm sorry. I was referring to the wrong. I was referring to the page we were doing. I was just gotten so confused here. Example 4, and by the way, that's at larsoncalculus.com for an interactive version of that type of example. But that was exactly the same as example 3, you know, and that's what I kept thinking I was turning to, and I was turning to 4. But you see, those are exactly the same answers here, okay? And I was referring to page 914, I should have been referring to page 913. But we do get the same answers for those. Because then I was looking at example 5 and said that's a totally different problem, and that's because it is a totally different problem. Those two, we first did it by substituting first and then taking our derivatives partials. The second we did the chain rule, and it comes out the same. Okay, so let's break from here. Sorry, erase my ink. Sorry. And, well, I thought I was going to erase my ink. There we go. Okay. All right. Then from theorem 13.7, which is what we did, we hold t constant, differentiate with respect to s. Partial of w with respect to s is partial of w with respect to x, partial of x with respect to s, plus partial of w with respect to y times the partial of y with respect to s. Not touching our t's at all in anything here, just dealing with the s's. And that will give us our partial of w with respect to s. And I had already gone and done all these individual partials, and all we do is put them together, and that would be the 2y times 2s plus 2x times 1 over t. But of course, you don't want the x's and y's in there. You want s's and t's, so you go and substitute what your x and y's are, and that's what we did. 4s squared over t plus 2s squared plus 2t squared over t. That would give you 6s squared over t plus 2t squared over t, and write that out as 6x squared plus 2t squared over t. Okay. Now there's not really any big reason for doing that, except it just makes it a little more concise answer. Okay. Then you do the same thing with the holding the s constant and taking the partial with respect to t, and you get partial of w with respect to x times partial of x with respect to t plus partial of w with respect to y times partial of y with respect to t. Plugging in those, and it's the 2y. That's the same partial of w with respect to x that we had before and partial of w with respect to y. So those come out the same. Then you have your 2t and your 2x times minus ts over t squared. That's your derivative partial of w with respect to t, because the t function had a 1 over t in it. That's where that comes from. Plugging in what your x's and y's are, then you get 2s over t times 2t, which would be 4s, period, the t's go away, plus 2s squared minus, minus 2s cubed over t squared, and then also a minus 2t squared. Okay. Yeah, that's how we did it. Then when you put it over t squared, the 4s over t squared too, you get 4s t squared added to the 2s t squared, subtract 2s t squared, it would be 2s t squared plus 2s cubed over t. And that's what we wound up with. And there you could factor out a 2s if you wanted to, but there's no huge advantage of doing it or not doing it. Okay. Now, so that's example 4. I'm not sure they do. Okay. The chain rule in theorem 13.7 can now be extended to any number of variables, just like we did in 13.6, I believe it was. For example, if w is a differentiable function of n variables, x of 1, x of 2, x of 3, all the way up to x of n, where each x of I is a differentiable function of m variables, t1, t2, t3, up to tm, then for w equal to some function of x1, x2 up to x sub n, you obtain the following, and you do each one individually, just as you get to them. The partial of w with respect to your first absolutely independent variable, t1, is the partial of w with respect to that first intermediate type variable, partial of x with w with respect to x1, times the partial of x1 with respect to t sub 1, and then go on through all the x's doing that, always with respect to t sub 1. Then do the partial of w with respect to t2, going through all the x's again, just like you did before, but this time the second of the partials in each pair will be the partial of x sub 1 with respect to t2, partial of x2 with respect to t2, and 3 with respect. So those partials with respect to t2. Then do it with respect all the way down to the t sub m, and that would then be the partial of w with respect to t1, x1 times partial of x1 with respect to tm, and then go on down, counting down all your x's and taking them with respect to your t's, the tm, the last one. All right, so they're going to skip example 5. Let's go back and we'll do example 5. Now, this time, sorry, having such trouble talking today. What we're looking for is partial of w with respect to s and the partial of w with respect to t. But this time, we've got some different players here. This is when s is equal to 1. Now that's not much of a variable, is it? It's a constant, okay? And t is equal to 2 pi. It's also a constant, okay? Now, where, that's not the whole problem, here's the rest of the problem, where x is equal to s cosine t, y is equal to s sine t, s sine t, I thought I left something out, and z is equal to t. Goodness gracious. Eyes are drying out, so I can hardly see the screen. I think it's because the fan, I'm leaning over where the fan is blowing the hot air up, and it's just drying my eyes out like crazy. Okay. Now, what we're looking for is partial of w with respect to s. Okay? I don't like the order in which they're doing this, okay? I would have said, written the whole problem down that you wanted to, and then said when s is equal to this and t is equal to that. The way they've written it now, it almost seems like you plug that in first and then start doing the other thing, and you really probably shouldn't do it that way, okay? So here's what we have. Partial of w with respect to s is equal to partial of w with respect to x times the partial of x with respect to s. Okay? Plus the partial of w with respect to y times the partial of y with respect to s, plus the partial of w with respect to z times the partial of z with respect to t. No, I'm sorry, s. I'm jumping ahead and doing my t's. Okay. S. Okay. Now, because you have 3 intermediate variables here, 2 independent variables, 1 dependent variable. Okay? cents. All right, so what we need to do is all of our still seems like we're missing something. Oh, there it is. I knew we were. This is 4. I knew I had something missing here. W is equal to XY plus YZ plus XZ. All right, there's your function. I was going to say we're missing something. All right, and again, I think it's a good first step to do all your partials just as you see them. Partial of W with respect to X is going to be Y plus Z. Okay? Partial of W with respect to Y is going to be X plus Z. And the partial of W with respect to Z is going to be Y plus X. Okay, believe I've got all those right. Okay. Now let's do the other partials. Yuck. Partial of X with respect to S is equal to cosine T. Oh my goodness, the 10 o'clock scholar. Okay, do you know if everything's been straightened out?
Yes, that's where I'm coming from.
Oh, I see. Okay. Okay. So.
That's the receipt.
Yeah. So so you should be back in the system now or soon?
No, now, because this is it right here.
Okay.
So because they have to put me back before I can pay.
Right.
So she put me back, and then they gave me this to go to the office and pay, and then
Okay.
so everything I should finish today. So
okay.
I should be,
Okay.
Should be
Well,
straight now.
what I don't know yet is whether I can see you in the system yet, or if it takes them a day or two to get. I know you're paid, but I don't know if you're going to show up on the roll yet. I'll see. I'll check this afternoon.
That part I didn't ask.
Yeah. Okay. I'll do. Oh, we've got a little bit of time left.
Yeah.
So let me. It's been sitting too long. My knee stiffens up. When there's no one in here, I just work on the screen, and I don't project on the board. When y'all are in here, then I point to the board, so I can get up and move around a little bit more. Okay. So, we're in Chapter 13, Functions of Several Variables. 13.5, Chain Rule for Functions of Several Variables. And we're now doing Example 5. Now, we did, just a little bit of review, I did Example 2, or I tried to, on page 912. But actually, as you look at that, if you got your book or ebook or whatever, and look at that, it turns out to be 4 different variables. And you have to do partials with respect to each one, and then each one of them is a derivative of another variable. So you have so many. So I just couldn't get everything on one screen, so I just referred you back to Example 2. So you have to do that basically looking at the book, because if I would have done it, it would have taken me 3 or 4 screens, and then I wouldn't have had the things to refer back to. But then we did Example 3 and 4, and now we're doing Example 5. This is on page 915. Okay. Now this isn't, they don't have it in the slide set, so here's what I've done. And oh man, Okay, I really dislike the way they've worded the problem. They say, find the partial of W with respect to S and the partial of W with respect to T when S equal 1 and T equal 2 pi. That to me should be the very last thing they tell you. I think this part shouldn't be in there, but they did it. For W is equal to xy plus yz plus xz when x is equal to s cosine t, y is equal to s sine t, and z is equal to t. Then I would have put for s equal 1 and s equal to t is equal to 2 pi. To introduce this now almost makes it think like you should plug that in right at the beginning. You can't. You have to take all your partials first with respect to the variables, and then at the end you plug in what they are. Because if you plug in now, they're all constants. You take a partial and it's 0. So, yeah.
Wouldn't that be a shortcut? Wouldn't that be easy to?
Yeah, but you wouldn't wind up with any answer. Because if you plug this in right at the beginning, right here, you would have, this would be 1, this would be 0, and this would be 2 pi. And then you do all this stuff, and they'll all be 0, because these would be constants. So you have to do the partials with respect to the variables, then plug in what the variables are. If you plug in the variables too soon, you don't have anything to take a partial of. They're all constants. So that's why I don't like the way. But, so here's what my recommendation is, and that's the problem. So the partial with respect to S would be, just like we've done, the theorems that we've had, partial W with respect to X, the first variable, times the partial of X with respect to S, plus the partial W with respect to Y, the second variable, times the partial of Y with respect to S, plus the partial of W with respect to Z, times the partial of Z with respect to X. And now, at this point, let's go back to this W and do your partial W with respect to X. Okay? And that would be Y plus Z, because these are both constants. Partial of that of constant is 0. Y plus Z.
So what happened to the mid term?
The what?
What happened to the middle one? Why it cancels?
Well, because when you're taking the partial of W with respect to one of the variables, X say, you count the other variables as if they're constants. Okay? You just treat them like they're constant. They're not moving. You're just taking the partial with respect to that one.
Since you were taking with respect to the X, so the Y could
yes, then this would just be some constant times X, and the partial of that would be the constant, right? This would be a constant times a constant, which is a constant, and the partial of that is 0. So that's why that went away. And the partial of this with respect to X would just be the Z, whatever that constant is. So that's why it's Y plus Z. And then the partial of W with respect to Y, which is going to be the next one you're going to need here, is X plus Z. And that's a constant, so that goes to 0. Partial.
Why we kept the first?
What's that?
Oh, okay, I see.
Yeah, okay. And then the partial with respect to Z, W with respect to Z, this has no Z, so that would be 0. This would be Y plus X. Okay. All right, that's where I was. And now we have to take the partial of X with respect to S. Well, here is X as a function of S and T. We're only taking with respect to S. So count the T as if it is a constant. So that would be some constant times the variable S, and the partial of that would be the constant. So that would just be your cosine T. Right?
Yes.
Okay. So let's pick up from...
Is that where now we're plugging the answers? Since we have
okay, not yet. Okay. We got to get it all worked out, and then we plug in. Okay? We probably could now, but let's... I'm afraid we'll get lost in the sauce if we don't keep it in order. Okay? So now let's do the partial of Y with respect to S. That's this one right here. And here is Y and S. So what would that be? That would just be sine T. Okay? And then we'll do the partial of Z. with respect to S. This one right here. And what would that be?
That's MT.
No, it's going to be 0. Yes, because that's a constant. That's going to be 0. Okay? So, let's plug in what we've got then. This partial of W with respect to S would then be the partial of W with respect to X, which is Y plus Z. We're going to write it like this. Y plus Z times the cosine T, partial of X with respect to S, plus partial of W with respect to Y, which is X plus Z, times sine T, okay, plus Y plus X, partial of W with respect to Z, times 0. So we could have left that one out completely, right? Because that last part is 0. Okay. But we don't want this expressed in X's and Y's and Z's. We want it in S's and T's, because those are your independent variables. So we'll go back and plug in what Y is, what Z is, and what X is in terms of S and T. So this would then be Y is S times the sine of T plus T times cosine T plus S cosine T plus, where am I? That Z plus T times sine T, okay, and that's it, okay? Now, at this point, that's when...
If it goes S cosine T plus Z plus 2 pi, because T is...
okay, yeah, now we're going to plug in what T is, yeah.
Okay.
Going to plug in what S, yeah, that's exactly what we're going to do here, okay? So this would be 1, okay, S equal 1, and sine of 2t is?
Sine of 2 pi is going to be sine plus 2 pi.
Sine of 2 pi is?
0.
0, okay, so that part is 0, and so this will just be 2 pi times the cosine of 2 pi, which is 1. So that's just 2 pi plus S, which is 1, times cosine of 2 pi, so that would just be, I'm sorry, 1. Okay, sorry. Okay, 1 plus 2 pi, but what's the sine of 2 pi?
0.
0, okay. So that's 0. So this is 2 pi when S is 1 and T is 2 pi. Okay. That just gets you that part. Then you got to go back and do the same thing for partial of W with respect to T. Okay? I'm real tempted to try to do it just by erasing. So if you don't mind, let me try that. That way I won't have to write as much again. Okay. So we're going to do this time partial of W with respect to T, and that'll be partial of W with respect to X times partial of X with respect to T, T, and T. So you see, a lot of it stays the same. Okay, that'll be the T, and what we have to do is come up here. No, let's change these. I think I could have left that one. All right, so let's go back and see what we have to do. Partial of W with respect to X is still going to be there. Okay, so this will be a T, a T, a T, and a T, and a T. Okay, now, see, that stays the same, right? Those three stay exactly the same. These three I probably need to change, so let me pull these off. It may be surprising how little they change, but let me. Okay. All right, let's try it. If I can keep straight what I have done and haven't done. So here what we need is a partial of x with respect to t now. Okay? What's the partial of x with respect to t? There's your x as a function of t.
It's going to be cosine t.
No. It's, you see, you're taking the partial with respect to t now. So s is a constant. And what's the derivative of cosine?
Sine.
Minus sine.
Negative sine.
Negative sine t. Okay? And the partial of y with respect to t would be,
Cosine t.
yeah, s cosine t. Because, see, that's an s there. It's hard to see. And the partial of z with respect to t is?
It's t.
It's 1. Z is equal to t. You see? Right here.
Oh, yeah.
And the partial of z with respect to s was 0, but the partial of z with respect to t is 1. Okay, so there is a difference. Okay? All of them are different, but that's one major. Okay. So, this is the same. Partial of x with respect to t is a minus s sine t, and partial of y with respect to t is s cosine t, and now I shouldn't have erased that. Partial of w with respect to z was y plus z, no, y plus x. I can't read my own writing. Times 1. Partial z with respect to t is 1. Okay? Got it?
Yes.
See that? Okay. Now. Okay. Now. Your y, I'm trying to find it here. There it is. Okay. That's s times sine t plus t, that's y plus z, okay, times s sine t. Okay. And then this one, the x plus z, I shouldn't have erased, but let's do it where it's, there it is. S cosine t plus t times s cosine t plus, and your x and y, x, okay, that would be s times cosine t plus sine t. You see, that's x plus y.
You factored it.
Yeah, I just pulled out the s because it made it easier. Okay, so there's your partial of w with respect to t in all of its parts. So now let's plug in s equal 1, t is equal to 2 pi. Okay, this of course is going to go to 0, right?
Yes.
So that one, but this will be 2 pi still. But this will still be 0, okay? So everything's 0 there. Here, this will be 1, right? Plus 2 pi times 1, right? So that's just 1 plus 2 pi plus 1 times cosine of 2 pi is 1, sine of 2 pi is 0. So what do we have now? 2 plus 2 pi. 1 plus 1 is 2. So, or you could have said 2 times 1 plus pi. I don't care how you write it. Okay. They left it as 2 plus 2 pi. Okay. So the first one, I'm sorry I've erased it now, was just 2 pi. And then the second one was 2 plus 2 pi.
You got it right there.
Do I?
You have the answer up there.
Yeah.
Yeah, right there.
Yeah, I know that's right. Oh, right there. Yeah, you're, no?
No, up there.
Up there.
You would
Right there.
Yeah, right there.
Yeah, I wrote it there. You're right. Okay, I forgot. Okay. And then this one is 2 plus 2 pi. All right. Whew. Okay. Now, we don't have much time for for implicit differentiation, but let's see if we can get it started. Okay. Implicit partial differential equation. This section includes with an application of the chain rule to determine the derivative of a function defined implicitly, not explicitly, but implicitly. Let x and y be related to the equation f of xy equals 0, where y is equal to f of x is a differential function of x, and to find dy dx, then you could use techniques discussed in section 2.5 way back. You will see, however, that the chain rule provides a convenient alternative. So let's consider this function. W is some function of x and y, which is a function of x, and y is also a different function of x. Okay? Capital F is a function of 2 variables, but the second variable is a little f of x. Okay. Now, that theorem 13.6 that we were just using, okay, notice we only have one independent variable ultimately now, so we can now talk about dw dx. Now this is 13.6. The one we were using was 13.7 where it had 2 independent variables. This is going back to 1. So dw dx, okay, is equal to f sub x, or partial of f with respect to x, times dx dx, which of course is 1, plus the partial of y with respect to, partial of f with respect to y times, as a function of x and y, times dy dx, which is this little f of x. Okay? Now, I wish this were on the same page. Okay, I'll let you write that if you want to.
One of the first one is ds over dx, and the second one is dt over dy.
Okay, well, okay. Here we have w is a function of x and y. But the y is a function of x, so another function, not capital F, but little f of x. Okay. So when you're taking the derivative of w, and it can be a regular derivative because both of these are the same x's. One variable, single variable. So dw dx, okay? That would be the partial of f with respect to x. That's what this is. That's a function of x and y. Times dx dx. Well, that's just 1, okay? Because that's only a function of x, okay? Plus, though, the partial of f with respect to y times dy dx. And that's what this one is, okay? Now, I know this is a bit strange. It's a weird way of expressing that, okay? Now, like I said, I wish this were on the same page as the top of the next slide. It would make more sense. But because w is equal, f of xy is equal to 0, now that's from up here, okay? Let x and y be related by this equation, f of xy is equal to 0, okay? And you might say, well, if that's equal to 0, derivative of this with respect to x, it's got to be 0, it would seem. But don't jump to the conclusion. I found this is not a very satisfying presentation, but they always do it. They always do this, okay? Because it looks like to me W would be 0. I mean, just from what they say, okay? But because W is equal to that, for all x's in the domain of little f, then you know that the W dx is equal to 0, okay? And you have that, okay, dW dx is equal to 0. That's, this one right here is equal to 0. That's what I said. W is equal to 0, so dW dx equals 0. So this thing right here is equal to 0. And you know this is equal to 1. So to find out what dy dx is, that's what we're looking for. If this one is not equal to 0, okay? If this one is equal to 0, then you don't have very much here. Then this has to be equal to 0. But if this one's not equal to 0, you can use the fact that dy dx, or dx dx is equal to 1 and conclude that dy dx is equal to minus, okay, now here's where this comes from. Solving for this, you move this to the other side, that makes it a minus f sub x, this, that's 1. Then divide by this and you get that. Now, a similar procedure can be used to find the partial derivatives of functions, several variables that are defined implicitly. That's a big sentence at the end, leaving us sort of hanging because I don't think we have room to follow it up. But this is just another way of finding a dy dx. It seems like it would have been just easy to take dy dx. But they're saying if these functions are sort of complicated, and that's not an easy thing to do, but it is easy to take their partials, then this is what it turns out to be. So you have to always go back and say, wait a minute, what is this really saying? And we'll come back. The examples we use, we'll emphasize those next time, but we're out of time now. But that's where we'll pick up with this theorem at the top of this page. And this is where we'll begin next time. We'll probably come back and review what we just said, but then we'll do examples 6 and 7. Okay? So homework exercises here, do either 3 or 5. They're both at calcchat.com. 3's at calcview. Do any of the odds 7 through 11. They're all at calcchat. 9's at calcview. Do 13. It's at calcchat. Do either 15 or 17. They're both at calcchat. 15's at calcview. Do either 19 or 21. They're both at calcchat. 19's at calcview. Do either 23 or 25. They're both at calcchat. Oh, wait. Hold off there. Just stop at 21 because we aren't going to find, we're going to do the examples before we do implicit differentiation. So we'll pick up and go from there. All right. Any questions? Okay. So I'll go